All right, students, let's start with Chapter 17, Wave Optics. First of all, what is light? It's interesting to study, and to me, I think um, light is probably the simplest phenomena that we have in our world, in our universe. And what I mean by that is it's something we see all the time. 24 hours a day, light is somewhere in our world. Now, I know you think, well, duh, but yet light can behave in a very complex way. And so something as simple and as common as light can be very complex, as you're going to see as we get into this lecture. And so light can behave in different ways. There are different models of light. We have three models. The wave model, which is one that's probably fairly easy to understand in that we see light as a wave. Here they tell you about water waves. Sound waves and water waves behave pretty similar. You know, we can use these same equations to find frequency and period and wavelength of a light that we can use for say, a mechanical wave. So that's an interesting, phenomena. And of course, we see lasers and other optical devices which operate off the wave principle. You can buy a laser and it'll tell you on the laser. You can buy them. I don't know if you can still buy them in the gas stations and these little stores, Y-marks and things like that. You can go in and buy them. You used to could buy them off the counter or on the shelf somewhere, these little laser flashlights. And I think they've banned a lot of those because kids are buying them and taking them to school and shining them in a teacher's face. And it'll tell you the wavelength on there, okay? But it'll also have a little warning on there, do not point in someone's eye, because it can be destructive, okay? All right, so we have the wave model, the ray model. When you look at prisms and mirrors, and optical lenses, telescopes, microscopes, it's better understood to look at light as a ray instead of a wave. Because of, and you say, well, how do you define it as a ray? Well, basically what you do is you take what is called a point of light, and you say, okay, from this particular point, the light ray will travel in a particular direction. Now, when you look at a light source, how many light rays are they? Well, there's an infinite number, okay? So, you know, for example, if you look at a light bulb in a lamp, there are infinite number of light rays going out in all directions. But as far as being able to understand its behavior and actually, I guess you could say, map it, a ray model becomes very useful for telescopes and microscopes and camera lenses and such, okay? However, there's also called the photon model. And we have, of course, the photon model, which helps us to understand the quantum theory of light. In other words, the particle theory of light. Now you say, well, how does this work? Well, we get into what's called the photoelectric effect. And if you've ever wondered how these little detectors on street lights work, or how a motion detector works, especially if it's using a laser, it operates on the photon theory of light, okay? Because photons are like little packets of energy. And of course, Einstein was one of the first ones to actually coin the dual nature of light. There's the wave nature, or their wave nature, and there's the particle nature, okay, of light. But we talk about the three different models of light. Now, of course, the properties of a light wave. All of you have watched light pass through an opening. I know if you've ever noticed something being projected onto a screen, You always notice around the edge of the screen you can see the colors of the rainbow. Well, that's because of the lens. The edges of the lens are actually diffracting the glass. Now, you can use, here we see an example where we've got two barriers with an opening in between them. And notice they're using water. Water is a good way to study the behavior of light because, again, what I said earlier about the properties of a mechanical wave are very, very similar to the properties of an electromagnetic wave, okay, which light is. All right, so notice it hits the barrier. Notice how they diffract, okay? Notice how they spread out when they hit the opening, okay? So this spreading out, or this, I guess you could say, it looks like it's bending, okay, is called diffraction, okay? And it's very obvious when we see this that light is being passed through an opening, okay? You know, like I said, one of the best ways to see it is if you're in a classroom and, you know, especially if it's good and dark, and they turn the projector on, right on the edges of the screen, you see the colors of the rainbow. Used to, when we had the overhead projectors, boy, I'm dating myself here, you say, what in the world's an overhead projector? Well, believe it or not, we didn't have computers when I went to school. Even when I was in college, where there were very few, there were not any used in the classroom at all. We had a few for lab, and I mean a few. Most everything was still done analog. There practically was very little digital, and so we had overhead projectors that the instructors would write on transparencies or a big roll of transparent film and project it on the screen, and you could see the colors of the rainbow around the edges of the screen because of the diffraction. Now, here again, we notice how if you make the opening much larger, notice how the waves do not diffract as much. So what does that tell us? That tells us that the size of the opening will depend on how much diffraction we get. And typically, the closer that the size of the opening is to the wavelength of light, then more diffraction we see, okay? All right, so, and that's what it's telling you here, and you can read this. Now, so let's look at light as an electromagnetic wave. Of course, it does consist of extremely fast-moving electric and magnetic fields, and we call this an electromagnetic wave. I'm kind of repeating myself here. And in a vacuum, and yes, this is one of those constants you need to write down, light will travel at 3 times 10 to the 8th meters per second, and that's in a vacuum, okay? So visible light then ranges from what wavelength? So it ranges from 400 nanometers to about 700 nanometers, and that's what we call the visible spectrum. And that's the wavelength of violet light, okay, to red, okay? Now, what is just below this? Well, UV is, and what's just beyond that? IR, infrared, okay? Those are invisible, okay? Unless you have a device to detect them. So, we can take our speed equation and do a little tweaking here, and we can find the frequency of any particular wavelength using this equation right here. The frequency is equal to the velocity times the wavelength, and that comes from our velocity equation, or we can say the velocity of a wave is equal to its frequency times the wavelength. Frequency is reciprocal hertz, or excuse me, reciprocal seconds or hertz, and wavelength will always be in meters. And so here they show you that if you take the speed of light and take a particular wavelength of visible light, you notice what the frequency is. Now, notice the relationship here too of frequency to wavelength, okay? The frequency, as wavelength increases, frequency decreases, or as wavelength decreases, frequency increases, okay? So it's inversely proportional to each other. Wavelength and frequency are inversely proportional. So, what does it mean when light waves pass into a particular medium? Let's say air, and yes, air is considered a medium. So as air hits glass, or air passes in, air hits glass, good grief. As light hits a piece of glass, or traveling through air and hits the glass, or light is traveling through air and hits the water, or it can be the other way. You could be in the glass and shine the light out into the air. You don't have to just come from air. You can go either way. Or be down in the water and shine the light out of the water, and the water will come into the air. So what happens is we see that the speeds of the material, the speed of light in each material is different. And of course, we know that speed of light in a vacuum is 300 millimeters per second, or 3 times 10 to the 8 meters per second. And so we take that and the speed of the light in the material, and we get something called the index of refraction. Now, if any of you have ever witnessed, say a spoon put in a glass of water, or a pencil, I know your instructors in school probably demonstrated this, and I still do this. I know it's a simple demonstration, but it's very applicable, okay? You can take a pencil and put it in a beaker of water, and it looks like the pencil's broken. You can do it with a spoon, you can do it with your finger, whatever. And why does it do that? Because the light waves, when they pass from the air through the glass and into the water, you've actually got 3 mediums there. And so you're definitely going to get some what we call refraction. And what is refraction? Refraction is the bending of light, okay? The bending of light, okay? Causing it to bend, all right? And slow down. And the light slows down. Now notice here that in a vacuum, that the index of refraction should be right at exactly 1. Now notice in air, and look, when we do these calculations, I always use that for air. I know that's 3/10,000ths, but hey, I still use it, okay? Water, 1.33. Glass, notice how glass is very high. Notice a diamond is extremely high, okay? So that tells you what happens to light when it hits a diamond, that it is extremely refracted. That's why diamonds, a good diamond, especially if it's been cut properly, will just sparkle in the sunlight, okay? But, because of all the facets, of course, and because of its index of refraction. And that's very high index of refraction. So the light waves are really slowing down, because you got to understand something. Diamond is really a piece of carbon, okay? It is not silicon dioxide like glass is. Okay, so then the frequency, notice this. Now, one thing we need to understand is that when light travels into another medium from one to the next, the frequency, you better remember this, does not change, okay? It does not change. Then how does it slow down? Because the wavelength is what is changing. The time interval is not changing, okay? Time is always constant. The time is not changing, therefore the only thing that can change is the wavelength, okay? The wavelength becomes shorter, all right? Okay? All right. Okay? All right. So the wavelength in transparent material, of course, is shorter than the wavelength in a vacuum. Very important to remember. You say, well, how do we get to that? Well, if you take the wavelength of material divided by the velocity of the light, divided by the frequency in the material, which is equal to the same thing as saying the speed of light times the index of refraction times the frequency in the material, which is equal to what? The speed of light times the index of refraction times frequency in a vacuum. You get this equation. If you want to know what the wavelength in the material will be, we'll take what the wavelength is in a vacuum and divide it by the index of refraction of the material, okay? That is how you come to that equation, all right? And so, yes, you can actually determine the wavelength of a particular color of light in a material, okay? All right, now, what about interference of light? Now, this gets a little complicated, and I'm going to do the best I can and make it, hopefully explain it to you to make it sensible, but you just bear with us. Okay, now, so, again, we've already talked about how when light goes through a slit, and again, remember what we said, the closer the slit, the size of the slit is, notice that's 0.1 millimeters, okay? 0.1 millimeters, not a millimeter, but 0.1, a tenth of a millimeter. So when you get a really small slit, notice you get a really good diffraction, okay? Notice how it really, really, really begins to diffract, okay? Why? Well, because the slit is getting close to, not real close, but closer to the actual wavelength of the particular light. So Young did his double slit experiment, and what did he show us? Well, he showed us that if you take two slits and based on the distance between them, you will actually produce what we call bright line, well, I won't call it bright line emission spectra. You get bright lines and dark lines. Well, now, what the heck is this? Well, what this shows us is that light can actually interfere with itself, or light can constructively interfere, or it can destructively interfere, okay? And so what happens then as they destructively interfere, notice what happens. If it's destructive interference, you get these dark slits. Notice where the destruction occurs. Notice it occurs right in here where the two waves meet. Bam, you got destruction here and here. Okay, see that? See, you got destructive interference here, and you got destructive interference there. Okay, all right. And so what happens is they cancel each other out. You get constructive interference right here. Notice that they add. Notice you've got the wave here, but then you've got another wave adding to it. Okay, just a little bit, but it's still adding to it. Okay, all right. Now, okay. So hopefully that'll help you to understand. Now notice right here what they call the central maximum. The central maximum is the midpoint. All right. The midpoint, and actually how you can define it is, it's the middle wave, okay? And again, when you do your, when you do your wave interference lab, you'll see what I'm talking about, okay? You'll see it, it'll produce these little wavelengths over here, and you'll notice the central maximum is your middle wave, okay? This is your central maximum, M, 0, and then of course as you continue to move above and below the central maximum, they number, of course, 1, 2, 3, 4, and so on. Notice how they get lighter as you get on out away from the central maximum. Well, that's because of the distance between the slits and, of course, how many slits you have. So notice that destructive interference is occurring where waves occur at positions on the screen for which R1 and R2 differ by a whole number of a wavelength plus half a wavelength, okay? And so that's helping you to explain, well, okay, I understand the black regions are interference, but how come? Okay, well, this is why. All right, let's move on. Now, so if you continue to look at the interference that occurs with a double slit diffraction, notice you have what are called the interference fringes, and those are the dark bands of light, so that's what we call them. We've already talked about the central maximum. And so when we want to start to do some calculations as far as, well, okay, what is R, what would be the change in R? And the change in R is the distance right here, the distance between the particular wavelengths, okay? So when you have constructive interference, then you have the bright fringes. And of course, that's going to be dependent on what? The wavelength and what particular maximum we're looking at, okay? Now, if it's the central maximum right here, if this was 0, then guess what you're going to get? Well, you're going to get a delta R of 0, meaning what? Well, okay, it means you're talking about right here. In other words, there's no separation between the particular wavelengths. So we find the positions on the screen where delta R is equal to M times the wavelength, and that's the wavelength of light. And notice we've kind of zoomed in on this, and to get you to understand what we're talking about. The path length R1 to path length R2, and so delta R is that distance in between there, okay? All right, so how do we find Y? Now Y, if we look at on page 541, Y is the distance from the central maximum to the first or to a particular, well, I can't even get it out, to a particular maximum, okay? All right, so you got M1, M2, M3. So how do we find that? Well, we can take the length, which is the distance from the screen. Okay, this is distance from the screen, and this is on page 541. If you want to see what these are labeled, it'll help you out. Page 5, what L is and what tangent is and everything. So, in other words, if I know my distance from my screen, if I know from here to here, okay, let's say my screen's there, from here to here, that's L, okay? I want to find Y. Well, Y is what? The distance from the central maximum to the next maximum, okay? All right, then I know that. If I know tangent theta, or take tangent of theta, I can find that. Okay, so we can find then the change in R, which again is the change in this right here, okay? Which is what? Well, notice it is this angle right here, okay? Okay, the difference in the path length difference. And remember, this is path length here and there. Okay? All right. You follow what they're doing there? Okay. I know I said I was saying it is in between, but here, well, it is. Okay. It's the difference in the path length. Okay. So notice the path length starts here and goes here and starts here and goes there. All right. Well, then boom, that angle right there, that's theta. Okay. So to find D, and what the heck is D? Well, D is this slit spacing. See, it tells you right there the slit spacing. All right. So to find D, then, if we find the change in R, then we know the distance between the slit spacing. And by the way, you're going to do this on your, and I'm going to tell you, your wave interference lab will really help you to understand this chapter better than anything, okay? And of course, along with your dynamic study modules, okay? So doing the lab, doing the modules will really help you to understand this, because I do admit it is difficult. It is a little difficult. I ain't going to say it's impossible, but it's a little difficult to understand, and it's a little difficult to explain too. All right, so we take this distance, sine theta, and we can find right here the difference in the path, okay? All right, and of course that's telling you where the bright fringes occur. So the center of the viewing string at Y is, of course, equally distant from both slits. Duh, okay, remember what we said, it's 0. And so therefore delta R is 0 and M 0, okay? Well, I've already said that. So as you move away from the center, the what? The bright fringe, the nth. Now, what is that? That's the maximum, whichever maximum is, M1, M2, M3. Bright fringe occurs where one wave has traveled M wavelengths farther than the other, and thus delta R is equal to right there. Now, folks, I hope you're getting these equations. And honestly, the equations you need to concentrate on, of course, are in your text. They're highlighted in yellow, and they should be annotated, okay? Most of them are. So, here we go. To find using small angle approximation, we can rewrite them and put our answer in radians. And so our whole number, whichever one it is, remember, if this was 0, then guess what? Theta is 0, okay? All right, but if M is 1, then you put a 1 here, the wavelength, and divided by the distance between the slits, and boom, you can get the angle in radians. And then, of course, you can convert it to degrees, okay? All right, now what about determining the distance y from the maximum? All right, well, take our equations and modify them a little bit, do some substitutions here, and we can find it this way, the whichever m it is. Of course, it's just 0, then you get 0. But if it's 1, then you get whatever you get, okay? All right, and of course that's in meters, all right, because it's distance. And so we can find then that the interference pattern is, of course, they're equally spaced. I hope you've already seen that by looking at these slides. And you will also see this when you do your wave interference lab, okay? And so then we can find the change in y, the difference from the maximum to the next maxa, by doing what? The wavelength times L divided by the distance between these slits, okay? All right. And so we can find then, analyzing double slit, you find delta R this way or this way, okay? All right, now, okay, so we're looking again at double slit. If we combine the previous equations, find that the dark fringes, now notice this is for dark, and what was this other one for? This is for bright. So notice there's a little bit of difference, okay? Notice that it is M plus 1/2, okay? So to find delta R, we've already said that in the previous slide, but now they put it in mathematical form. So it's M plus 1/2 times lambda, okay? And again, when you do your wave diffraction lab, you'll see this. You'll see this property show up, this relationship, show up, okay? All right, now, so for dark fringes, there it is, okay? All right, so the intensity of light, of course, oscillates between dark fringes where the intensity is 0 and the bright fringes are maximum intensity. And of course, as you note, as you get out farther from the central maximum, the intensity of the bright fringes does get lower, okay? All right, now what about diffraction grating? So diffraction grating, again, is a multi-slit device. Some of you probably, and I used to and I still do sometimes, I have little pieces of diffraction grating on little slides, looks like projector slides, and you don't even know what I'm talking about, do you? Projector, the old mechanical type projector, you could have slides made of photographs. They're probably about a, 2-inch by 2-inch square, something like that. And it went in the machine and it go when you mash the button to turn the slide. Anyway, boy, that is going old school. Buy them in an antique store or online or something. But anyway, diffraction grating, you can get it in those little slides, and you can look at light and see what happens to various colors of light as you look at them through a diffraction, and you will be amazed. Basically, it's the same thing as a little spectroscope. If you've ever had one of those handheld spectroscopes, we have some here at school, and we will look at different wavelengths of light through them and analyze them, okay? And that's basically what we're building to. So the diffraction grating looks something similar to this. And again, it doesn't necessarily always have to be a slit, but it can be in other words, an actual opening. But it can be like, for example, you take a piece of film and you put marks on it. You scratch them. Well, anytime you put a depression or a mark on that piece of plastic, what it does is it causes the light wave to diffract, okay? Just like I told you earlier about the old the projectors, when you're looking at a projector screen along the edges. Why does it do that? You see those colors? Well, it's because the edge of the lens light's going through the edge of the glass, okay? Okay. Of course, your near projectors, you don't see it quite as much, but the old overhead projectors, you could, okay? All right, so notice that as the waves are pretty much parallel to each other, okay? Notice how they pretty much follow a parallel path. And so what does this enable us to do? Now, the relationship is still pretty much the same as far as finding the angle. Notice that it looks very similar to what we've already looked at. So if we want to find, if we have n number of light waves, and how many is that? Well, it could be infinite if you wanted to. And from n different slits, well, what does that mean? That means you can have a tremendous number of slits or a smaller number of slits, just based on how many ever slits you have. They will, of course, all be in phase with each other when they arrive at a point on the screen at a particular angle, okay? All right, and so we can find this. We can find that if we want to find what the angle is, then we can rewrite this equation. Or if we want to find out what D is, the distance between the slits, we can solve it that way too. Notice the relationship here of the particular maximum times the wavelength, and of course notice it's equal to d sine theta. All right. Same way with y. Notice it changes a little bit. However, we use what? Tangent of theta to find which particular maximum we're talking about and how far from the central maximum, okay? Because remember, Ym is central maximum, and so if we want to find Y1, Y2, Y3, then that's how we calculate it, okay? All right, so notice here how the fringes, as you get farther and farther away, notice how they get smaller and smaller and smaller and smaller, but they also get brighter too. So notice that as the number of slits increases, the fringes get narrower. So if you increase the slits, okay, notice it gets thinner and brighter, okay? Now, why is this important? This is extremely useful if you've ever heard of spectroscopy or gas emission spectroscopy. You ever wondered how on CSI, how in the world they know that, that fire was arson? Because it just, the house burned. How do they know it was arson? Well, they take samples and they analyze them, and based on the particular, when light passes through that sample based on the compound, it will scatter or diffract a particular way when the light passes through a prism or through a diffraction grating. And guess what? It will show you the actual chemical compound based on the particular fringe pattern you get for each particular element. All right, so spectroscopy, I'm getting ahead of myself. We're measuring those wavelengths. We are studying and measuring them at the atomic and molecular level, okay? So as I said just a second ago, each particular element on the periodic chart has a unique spectra, and you can use either what is called bright line emission spectra, dark line emission spectra. Again, it's going to look something similar to this right here. All right, now, again, why is this important? Well, I've already given you one example. If you've ever wondered how in the world do the astronomers know that that star is predominantly hydrogen or that star is burning predominantly helium, They take the light from that star, pass it through a spectroscope. I'm very sorry. That was supposed to have been on vibe, and it's not. Okay. Hang on, I'm going to have to pause. Sorry about that, folks. Okay. Children calling me. All right, so how do they know that the star, I did turn it on, yeah. How do they know that the star is made of helium? Well, they take the light from the star, pass it through a prism or a diffraction grating, and it will separate into its predominant characteristics or predominant colors. In other words, if it's mostly helium, then guess what? It will produce an emission spectra that is for the element helium. And so they analyze that and they say, well, you know what? Mostly what spectra we see here is helium, okay? And that's how it's done. All right, let's move on, okay? And again, they're showing you that, basically what I'm talking about, all right? They talk about reflection gratings. Thin film interference is very much like the same of what we've already seen. If you've ever wondered how you get, notice here you get the interference of this, notice this candle here. Even air can act as a, can cause interference. Notice this, the light is partially reflected not only from the front surface of the sheet of glass, but also from the back surface. So notice here you get interference there. Thus, why you have two reflections, okay? Now, so what happens to light? Now, we've already talked about this. When it hits a boundary, it does slow down, okay? So if you go from air to a medium, or it doesn't matter, or medium back to air, it is going to either slow down or speed up. If it's going back to air, it'll speed up. Why? Because the index of refraction is lower. So the index of refraction is going to increase, and that definitely will have, if you have an index of refraction that is higher, it's going to definitely have an effect on how well the light will reflect or not reflect, okay? And it all depends on the index of refraction, okay? And I'm going to move on. That's, again, just some of the same. Here we have, if you want to find out the conditions for constructive interference with either 0 or 2 reflective phase changes, this is how you can find it. T, of course, being the number of interfaces, if I'm not mistaken. Yes, okay? So let's move on. Again, notice how air, if you sandwich air in between two pieces of glass, notice how it produces bright and dark line fringes, okay, because of the interference. Same reason why the bubbles produce certain colors. Notice you get particular colors produced. Why? Well, if you use the equations, you can see why and see what color you will get. All right, single slit diffraction. Notice if you have a single slit diffraction, your central maxima is always very large, okay? And then, of course, the secondary maximum are not as strong and not as visible, okay? Notice how the dark fringes get larger as you move away from the central maxa, okay? And the bright fringes are not as bright, and they get a little narrower, okay? All right, so Huygens principle basically says what? We're looking at how we extend the propagation of a particular wavefront. So his principle has two parts, that each point on a wavefront is a source of a spherical wavelet that spreads out at the speed of the wave. In other words, it can kind of, and this is to put it in layman's terminology, it can actually act like its own source of light. It can act kind of like a point source, okay? And at a later time, the shape of the wave front is the curve that is tangent to all the wavelets, okay? So based on the wavelets, okay, the tangent of the wavelets, it will depend on your next wavefront, okay? Or what we call the wave plane, okay? So you have an initial wavefront, the curve tangent to the wavelets of a spherical wave is a larger sphere, okay? Then you have a second wavefront, and notice where we tangent. Well, here, tangent here, and here, and here, and here, and so on, okay? All right, now, all right, so looking at single slit diffraction, we find the theta P, and P, of course, is the particular maximum. And if you look at page 553, you see these equations, 554. Okay, so we can find the angle in radians of dark fringes in a single slit. I don't know why I keep saying that. Single slit diffraction with slit A, which is, of course, the width of the slit. And again, this is the dark fringes. Okay. All right, now where are your dark fringes going to be? Here, and here, and here, right? And here. And this should look very familiar to your wave diffraction lab, okay? So your dark fringes, and there'll be another one here, and be another one there. And so your bright fringes, what? Bright's right here, and there, and there's your central maximum. Bright, and bright right there, okay? All right, and so we can find that width, and we can find the length, okay, to the maximum, from the maxa, using this equation. All right, now, the width of the maximum, in other words, how wide will the maximum be? Well, 2 times the wavelength times the length from the screen divided by A, okay? So notice the smaller the opening a wave squeezes through, the more it spreads out on the other side, okay? Remember, I've already talked about that opening needs to be closer to the actual wavelength to get the effect, okay? I hope this helps.